Hi, welcome to my video on differential equations. This is going to be a little different, lecturing to a camera, so I'm going to try to do my best. So first off, I want to start off with what is a differential equation? Well, differential equation is basically an equation that involves a function and its derivative. So usually you'll find a function with its derivatives in it. So for example, we have now you can see that there is a derivative here, and so this would be considered a differential equation. Now this derivative, this is order 1, and you can see it's order 1 by the prime, and so here we have our function. And we're going to figure out how these two components are important to the differential equation. So that's one thing to know about differential equations. The second thing is going to be the solution. So the solution is a function that satisfies the given differential equation. So like I said, the solution is a function that satisfies the given differential equation. So sometimes you'll see D.F.E, usually means differential equations. And to solve these differential equations, there's going to be many methods. There's many methods to solving a differential equation. You're going to figure out that there's going to be so many that you can't even remember some. But there's easy tricks to remember them, so I'll help you out with that. So next we classify them. Usually we'll classify them by ODE, which is the ordinary differential equation. Ordinary differential equation. And some are going to be partial. So that's partial differential equation. Okay. And then next we'll see that it's also classified by the order. So like I mentioned before, order. Now you have you could see it as dy over dx or y prime. Well, now this is going to be order 1. Order 1. Now you can also see dy over dx. Now this is going to be also seen as y double prime. Now the order is going to be order 2. So that's going to be a way to classify a differential equation. because later we're going to see that we could solve differential equations of order 2, 3, 4, and anything higher. So another way to classify them is, let's go back over here. So another way to classify them is by linearity. I hope that's a word. So you'll have linear differential equations, and you'll also have nonlinear differential equations. So the linear is going to be in the form of anx y n plus an minus 1 x y to the power 1 to the power of n minus 1, and that's going to go plus. And I hope you guys can see the pattern. Now this is going to equal a function, and I kind of made this really big, so let's just draw a little arrow. So just to recap, the linear differential equations are going to be in this form, and then our nonlinear equations are going to be not linear, to state plainly. They're just not going to have this form, right? Okay. Okay, so let's just look at a couple exercises. So we'll have, oh, and by the way, I use the differential equations edition 5 book. I know there's like an edition 10, but I really trust the 5th edition. It's really simple, and I like how they explain the concepts. So let's go to example 1. So we'll have 1 minus x times y double prime minus 4xy Okay, so we're going to try to find if this is linear, nonlinear, and what order it is. So if we look at this, we want to look at the highest order. So it's definitely not the first one. It's going to be the second one, second order, because of the double prime. So we could say that this is second order. Right? And then, is it linear, nonlinear? Well, we have this function, and if you go back to the format of the linear differential equations, you'll see that this is, that was a check mark. You'll see that this is linear. Okay? So, let's look at number 2. Let's look at a different example. Okay, so number 2. Now this one's an important one because one, it shows you a different way to write the derivative, but it's crucial to understand the difference between orders and powers. So what would be our order for this differential equation? Well, it's going to be a third order. And why is that? And how come it's not 4? Well, this is the order. This is the derivative, the third derivative. And this over here, this is a power. So that's the exponent. We have this single derivative, which is order 1, raised to the 4th power. So that's going to be the difference. So it's going to be third order differential equation. And also, is it linear or nonlinear? So it's going to be nonlinear. And why is that? Well, because of this. It's equal to 0. If we looked on our format before, you'll see that nonlinear is usually equal to 0, and linear is equal to a function. Okay? So let's look at a different example. And if I'm going too fast, you could go ahead and go back. Obviously, this is YouTube. So yeah, let's do number 3. Number 3 says y times y prime plus 2y equals 1 plus x squared. All right, so let's figure out what order this is. So if we look, it's going to be first order, right? And is it linear or not linear? Okay, so now this one you definitely have to be careful with, because our coefficients here, our coefficient here is y, right? So that's going to be nonlinear. So why is that? Well, because we can't have y as a coefficient. You can't have y as a coefficient. You couldn't have x as a coefficient. You'll figure out y later. So that's just seeing it for right now. This for number 4. Number 4, this one's a lot trickier. Kind of spoiled that. Okay, so you don't see any, wow, I really spoiled that one. Okay, so without me trying to spoil the answer, you can see that this equation, it looks a lot different than this one because it doesn't have its derivative clearly seen in the equation. However, because I spoiled it, you could see that you can divide every term by dx. I'll humor you by dividing dx to that 0, which is really what you're doing, but we all know what it is. Now you have x squared dy dx. There's our derivative. And then here, we'll have our dx cancel, right? So now we have this y minus x times e to the x equal to 0. Now it becomes a little more clear, right? So now our highest power, our highest order, excuse me, is going to be first order. And then, is this linear or nonlinear? Well, we have to be careful because by adding that to the other side, we have, let's see, well, we could see that we could factor out a y here. So if we do that, we're going to have this 1 minus x. And then this is going to be equal to x e to the x. So now this goes from a nonlinear differential equation to a linear. Good. Okay, so hopefully that becomes a little clear as you go through more examples. Okay, so the next thing you might come into contact with is verifying differential equations, verifying their answer to the differential equation. So let me just show you what I'm talking about. Sometimes you'll see dy over dt plus 20y equal to 24. And then you'll have y is equal to 6 over 5 minus 6 over 5 e to the negative 20t. Let me just rewrite that. That's a negative 20t. And if we see here, what this means is, what you want to do is, so we have y here, and we have y. If we plug that in, we should get the both statements equal to each other. And if they are, then this is an answer for the differential equation. And notice how we have a y prime here. We have a y prime here. So that means over here, we're going to have to take the derivative. So if we implicitly take, I'm sorry, we're not going to implicitly differentiate that. If we take a derivative of y, we're just going to have that times that, okay. That's a negative 20t. Okay. So now we have our y and our y prime. And I guess we should write it like this to see better. So we can go ahead and plug this in. That's going to be, and our y is that. Equal to 24. Okay, so all I did was take the solution, took the derivative of it, and if you know how to take the derivative, I was looking at my paper to see what the answer was. Well, this is a constant, just goes to 0. This is the power rule, so that's going to do that. Did I say power rule? I just meant take the derivative of this, which is going to be 6 over 5 times negative 20 e to the negative 20t. You'll see that we have a negative 4. So that's going to be equal to negative 24 e to the negative 20t. And that's how we get our y prime. Okay, so we're going to distribute that 20 there. So now we have plus 24 minus 24 e to the negative 20t, right? Let's see if I did something wrong. Oh yeah, my derivative. It's supposed to be a positive. Okay. Now, these terms right here, they're going to cancel out because we have a negative and a positive. That's what I was wondering, because they were going to have to cancel out. So now we have positive 24 is equal to positive 24. So we could see that y equals 6 over 5 minus 6/5 e to the negative 20t is a solution to this differential equation. So that's going to be, those are going to be the types of problems you might see in the beginning of the chapters. Okay. Okay, so now we're going to be talking about the different types of ways of solving differential equations. So like I mentioned before, the methods, we're going to go through one method. This method is called, if you're following along in the book, in the 5th edition, it's going to be Chapter 2, Section 2. We're going to start off with separable differential equations. Now these are pretty cool because they're going to be the simplest types of differential equations that you could see, and it makes differential equations fun. So let's go ahead and look at one problem. So our first problem is going to be dy over dx equals to y plus 1 over x. Now, when I was taking the course, this troubled me because I didn't know what was going on. But essentially, we're going to get this. How do we get that? Like my professor said, we don't have time to explain it. I'm just kidding. So what I did was, if you didn't follow, you're just gonna get this. So now you have okay. Oops. Okay. So now that you have this, and basically what I did was a computation up there. Hopefully you could see what I did. And if you didn't, well, you could just okay, so number 10 we'll do dy over dx equal to y plus 1 over x. So basically what's going to happen is we're going to have this and this switch positions, and this switch positions. So we're going to have dy over dx. Okay, and so now to do our next step for the separable differential equation, we're going to take the integral of both sides, and if you see, this is going to become the natural log of y plus 1 equal to the natural log of x plus c. Okay? Now, this is really important because that c indicates that it can have many solutions, so it's not unique. And by unique, I mean there's not going to be an IVP. And we'll learn what IVP means. Okay. And so basically, that's our answer. And that's how you solve a differential equation separably. Okay, so let's see another one. Let's do number 14, which is EX. Oh. All right. So if I were to ask the question, which order is this differential equation? The correct answer would be 1, because we have that first order differential equation. Okay. So now what we could see from here is that we could split that up. And that's going to be e negative 2x times e negative y. And if you could see, y split that up. That's great. Well, now we have these two like terms. And so now what we're going to do with that is we are going to factor it out. Okay? So then what we're going to do is multiply both sides by dx. Okay. Now I have ex dy is equal to so after I multiply dx to both sides, I get this. Okay, so if we could see this, if we look at this, we know that e to the negative y power could also be 1 over e to the y. So that's something good to see. So eventually, if we were to do the computation, we're going to get ey y dy equal to e to the negative x perfect. So now we have our y's with our dy and our x's with our dx. So then the next step on solving the separable differential equations is to take the integral of both sides. And if you notice, and if you're not too good at this, we're going to have to use we're going to have to go through the integration by parts. So if you don't know the formula, it's the integral of u dv is equal to uv times the integral of v du, right? So we can make our u, y, our du, 1 after you take the derivative, our dv is going to be ey dy, and the derivative of that is simply going to be that. Okay. And if we were to do our integration, we should get, the answer of, oops, so this is going to be one of our hardest separable differential equations, simply because we have to think back to a topic that we learned in one of our previous calculus classes. So, shouldn't be too bad. So let's say, for instance, we had xy prime equal to 4y. Well, what I would do first is divide the x to both sides. My x's will reduce. I am now left with y prime is equal to 4 over x. Now, that probably doesn't look easier, but if we remember, our y prime also equals to dy dx. Now, what I want to know, what I'm thinking right now is, how do I get our x's with our dx and our y's with dy's? So that's basically the main question you should be asking yourself. Well, you could go different routes. I'm just going to multiply by dx to both sides. Now I have dy is equal to 4yx dx. Okay. So now how would I get y over here? Well, I'll multiply both sides by 1 over y. Oops. All right, so I'm going to cancel these y's out. So now what I'm left with is 1 over y dy is equal to 4 over x dx. Okay, and so the next step for solving separable differential equations is going to be take the integral of both sides. All right, so the integral of 1 over y with respect to dy is going to be the natural log of y. And this one, that's going to be 4 natural log of x plus c. Okay. And now, according to our log rules, if we start from here, we have natural log of y is equal to this. This is going to become an exponent. Right? And now, something pretty important is that this c, like we said before, could be any number because it's not unique. So what we can say is this. So this is any number. This is any number because it could be any number. It's not unique, like I said. Now, it can be a little clearer as to what we're trying to do now. According to our log rules again, addition means multiplication. Right? So now if we take the e both sides, we'll have y is equal to c x to the 4th. And so that's going to be our answer. So this is a good one because at the end it brings back some of the log rules, and that's a good practice. If maybe your algebraic skills are not up to par right now, they could be after this problem. You'll see why. And it's good to see this problem because it'll test your algebraic skills. So in the book, it's going to be number 34. We have dy. Actually, we should probably move it over. We have dy over dx is equal to x times y plus 2y minus x minus 2 over x, y minus 3y plus x minus 3. And if you're thinking, oh God, what do I do? And how do I solve this using the separable differential equation method? Well, that's going to be simple if we just rearrange stuff. So if we rearrange stuff around, we could see that that term has a y, this term has x, right? So if we see that, this also has a y, so we could we could take that, we could factor out that y. And we could factor out a negative. Can we do that? Yes, we could factor out a negative from here, and then we get that. If you're wondering why, if I were to factor this negative back in, that'd be negative x, and that would be negative 2. Okay? So now, if I were to factor out my y from this one, I'm going to get y, x minus 3. I could just leave that if I wanted to. It's probably smart. I don't think there's much you could do with that. Okay. Okay, so now what you could do is you could see that dy dx is equal to x plus 2 times y minus 1 over x minus 3 y plus 1. So what you're going to do now is multiply by the reciprocal. If you don't see how I got that, it's basically like factoring. So I could factor out a x minus 3 from here, from this denominator, and now I have y plus 1, right? And then times x minus 3. If I were to factor out x plus 2 from the numerator, I'm going to get x plus 2 times x minus 1, right? So that's how I get this simplified version of it. Okay? So now if I look at this, I'm looking at this now because it's striking my eye. I'm going to multiply by the reciprocal to both sides. Okay? So by doing that, I'm going to get this oops. What did I do? Right, and multiply by dx. I could do that. I could either multiply by dx both sides first, or I could do the reciprocal. So I'm just going to do the reciprocal. Okay. And now you can see that these will cancel out. And then at the same time, I'm going to multiply by dx to both sides. Alrighty. So now what I have is y plus 1, y minus 1 times dy equal to x plus 2, x minus 3 dx. And if you see, now I have all my x's in the same place, and that's the only time you should have your x's in the same place. And you also have your y's in the same place. Make sense? So it's going to be easier, somewhat easier to integrate. Lost the word. So I could divide here, right? And I get and if I divide here, I'm going to get now I divide them simply because it's going to make it a little easier on me. to integrate. So if I divide that, that's how I would divide it. Same with here, I would divide like this, and then I would get this. Okay. And then, now I'm going to take the integral of both sides, right? Integral of both sides. And that comes out to so yeah, this one is it's a good problem. If you want to know how I got there, well, I'll tell you. If I take the integral of 1, I get the y. If I take the integral of 2 over y minus 1, I'm going to get this 2 times the natural log of y minus 1. That becomes the argument. And then that's going to be equal to the x from this 1, right? Times 5, plus 5 times the natural log of x minus 3. And then plus c because can't forget about the solution. Okay? So this is our answer. We can go ahead and box that and get full credit. Okay. All right, so let's look for a juicy problem. I guess this one's good. It's pretty long. Ah, this one's a really good one. So in the book, it's going to be number 58. If we have dy dx equal to 1 minus x minus y over x plus y, so what should we do first? Well, I could see that we can make part of the numerator same as the denominator. So how would I do that? Well, I could factor out that negative and have x plus y over that. So now we have these two pieces equal. So we could say that u is equal to x plus y. Now the only time that you could do this is if the x and y's are like this. Okay, so we now have dy dx is equal to 1 minus u over u, right? We also have to take du over dx, and that's going to equal 1 plus dy dx, right? And so now we have to solve for dy. So how do we do that? Well, we just subtract 1 to both sides. And now we have dy over dx equal to du dx minus 1. Great. So now we can plug that in. Du over dx minus 1 equals 1 minus u over u. All right, so what do we do now? I guess that's a good question to ask, because I have no idea. Well, if we look, this could also be seen as this. Right? Because they're both over u. So now we have du. I like to write out all the steps. It lets me see where I'm at. Most people will skip steps. That's okay. For me, I like to see how it all pans out so that if someone else saw my work, they'd be like, oh, okay, I can follow the steps. Because people are all about steps and order. Okay, so now if we have this equation, well, I can now add 1 to both sides and have du dx equal to 1 over u. Wow, okay. So now my variables are u and x. Well, basically going to swap positions. So if we go back, now they're going to become, let's see, u dx equal to dx. Whoa. Okay. And now if I were to take the integral of both sides, well, I have 1/2 u squared is equal to x plus c. And now something to remember is that this u needs to be in terms of x and y. So if we go back in the past, take this u, plug it into there. Ta-da! Box this answer, get you 150 points on the exam. Sure. So there we are. It's a little good problem right there. So now we did separable differential equations, or we could do one more, and now this involves a lot of trig. So now number 60 in the book. Right? So number 60 says dy over dx is equal to sine with the argument x plus y. And like I said before, x and y have to be together in order to do that u substitution. So u is equal to x plus y. We can say that. So now this argument becomes u. Okay, well, what does that mean for us? Well, if I rewrite it, it makes it a lot cleaner. Well, like in our last problem, we have to solve this equation now. We need to solve it in terms of dy dx. So if I take the derivative of u with respect to x, we get du dx is equal to 1 plus dy dx. Okay? Now we got to solve for dy dx. Wow. Just like last problem. That's a d. minus 1 is equal to, doing it all backwards, is equal to du dx minus 1. Okay, so now that's great because we could plug it back in. We can plug it in here. Now we have du dx minus 1 equal to sine u. Okay, so now what do we do? Well, if you know how to add, we could add 1 to both sides, right? And now we have du dx equal to sine u plus 1. All right, now what do we do now? Well, you want to get your u's in the same place and your x's. Well, we don't have any x's over here, so we can just get rid of our dx, put it somewhere else. Dx. Right? Okay. All right, so now we have du. This is me writing out all my steps again. Okay. Well, how do I get this u over here? Well, certainly by magic or division, whatever you call it. Great. Now I have my u's on one side. Should I write it again? Yeah, sure. Equals to dx. Great. Okay, perfect. Now what I want to do is take the integral, right, of both sides. Well, this one's going to be simple. The integral of simply dx is going to be a beautiful x. And we can't forget about our plus c, because we got to bring that plus c along. All right. So now how do I haven't integrated this yet because I'm going to manipulate it. Okay? So by manipulate, I mean I'm going to multiply by the conjugate. Okay. Okay. Great, great. So let's not forget about, let's see, this guy. Now that guy's pretty important, especially in this problem. Because if you look here, we're going to get 1 minus sine u over 1 minus sine squared u. And this is just the perfect square. So basically we have that 1 squared. That's the difference of squares. So we have that 1 squared, which is just 1, minus the sine squared of u. Okay. Oh, and we're going to employ that. So now we have 1 minus sine of u over cosine squared u. Great. It's great for us, right? Okay. And hopefully that lets you see a little clearer as to what we're trying to do. This is being divided to both these terms, so now we have 1 over cosine squared u minus. Great. And by manipulating it, this is exactly what I meant. Right? So if we're going to take the integral, of that, finally. This is already integrated. We're going to get a nice secant squared u plus, well, if I said basically what I'm going to do is a u sub to integrate this, but I don't want to use a u, so I'm going to use a v, right? So dv equals to negative sine u du. So now what I'm going to have is 1 over v squared dv. Okay, so great. What does that mean? If we integrate that now, we're going to get, still we have to integrate that because this was basically secant. Forgot to mention that. And now we get tangent u, and that's an integral of secant squared u, right? And then this is going to be minus 1v equals to x plus c. So now that we integrated secant squared u and 1 over v squared, we get that. And then we're done for right there. So we need to go back and input all our u's. Okay, so this one, this tan u, the tan u is going to become tangent of x plus y minus v. Okay, so v was cosine u, so that just means our u was x plus y, so cosine x plus y. Equals to x plus y. Oh, x plus c. And boom. So a long process, but got us to the answer. Whenever it comes to trig, when you see trig in a problem, you might think to yourself, I might have to manipulate this. And if you know your trig identities, it'll become a lot more clear as to what you should do in the problem. Okay, so let's put that problem aside. And let's look at another method, because that will complete our separable ta-da, that's going to complete our separable differential equations. We can now move on to another.